Soda goes flat the second the bubbles lose interest in you.
Well, actually...
Right now, picture 2 drinks on a table. You crack the first one open, and it hisses, climbs the glass, and stings your tongue like it is alive. You open the second, and it sighs, sits there, and is flat and sad by lunchtime. Same shelf, same little bubbles, same word on the label, carbonated. So why is one of them so much fizzier than the other? You already think you know the answer, and the answer you are about to give is wrong. So let us watch it happen. Most people believe fizziness is one simple thing. A fizzier drink just has more gas crammed into it, more bubbles, more of the stuff. Well, actually, fizz is not one thing at all. It is 3 completely separate things wearing the same costume. How much gas is dissolved in there, how fast that gas can get out, and how much tingle your tongue even reports back to you. Those are 3 different knobs, controlled by 3 different forces, and almost none of it is happening where you think it is. Change any one of them, and the exact same soda can feel like a different drink. Start with the first knob. How much gas is in there? This one obeys a law that is over 200 years old. In 1803, an English chemist named William Henry worked out that the amount of a gas you can dissolve into a liquid depends directly on the pressure of that gas pushing down on it. Squeeze harder, and more dissolves. That is the entire secret of the factory. A bottling plant forces carbon dioxide into the liquid under high pressure, so a huge amount dissolves and hides in there, invisible. Then they seal it. When you crack the lid, the pressure above the liquid suddenly drops to normal air, and the deal is off. And all that gas that was being held down starts fighting its way back out. And here's the thing. Different drinks are packed to different pressures on purpose. A cola is pumped far fuller of gas than a beer. Brewers and bottlers even put a number on it, something they call volumes of carbon dioxide, which is roughly how many bottles worth of gas has been crammed into a single bottle of liquid. A typical cola runs around 3. A lager sits closer to 2.5. A German wheat beer can be pushed all the way up near 5. That one number, chosen at the factory, quietly sets the ceiling on how fizzy a drink is ever allowed to be. So some drinks really are fizzier by design before you ever touch them. But temperature quietly moves that same knob in your kitchen in real time. Cold water can hold far more dissolved gas than warm water can. So a cold soda is sitting comfortably, holding its gas with room to spare, and it lets it go slowly and politely. But let that same can get warm, and suddenly the liquid is holding more gas than it is physically allowed to at that temperature. It is over full. It is desperate. So the instant you open a warm soda, it does not sip its gas out. It panics and erupts and foams all over your hand. Same soda, same amount of gas, opposite behavior. The only thing that changed was the temperature. Now the second knob, and this is the strange one. How fast the gas escapes has almost nothing to do with how much gas is in there. Because here's a fact that sounds impossible. A bubble cannot just appear out of nowhere. Forming a brand new bubble in the middle of a smooth liquid is genuinely hard. The water clings to itself, and the surface tension fights to keep any bubble from being born. So the gas cheats. It looks for help. It looks for a tiny rough spot, a scratch, a speck of dust, a fiber, a place where a little pocket of air is already trapped. Those are called nucleation sites, and the gas can only grow a bubble on one of them, which means a scratched, dusty glass will fizz like crazy, while the exact same soda in a perfectly smooth glass will sit there almost calm. The fizz you're watching is not really about the drink. It is about the surface it happens to touch. This is also the answer to the oldest myth in the refrigerator. You have been told that shaking a soda builds up the pressure inside, so it explodes when you open it. That is not what happens. Shaking barely changes the pressure at all. What shaking actually does is whip the gas into thousands of tiny microbubbles suspended all through the liquid. And every single one of those is a ready-made nucleation site. So when you crack the seal, all of them let go at once, and it erupts. Let the shaken can just sit for a while, and those little bubbles quietly rise and dissolve back in, and it is safe again. You never had to release pressure. You only had to wait for the nucleation sites to disappear. And if you want to see nucleation taken to its absolute limit, drop a Mentos into a bottle of diet soda. In 2008, a physicist named Tanya Coffey at Appalachian State University actually studied this and published it. The candy is not reacting with the drink chemically. Nothing new is being made. Under a microscope, a Mentos is covered in millions of tiny pits and craters, and roughly 100,000 of them go to work at once, each one a launch pad handing the trapped gas an instant escape. The whole drink dumps its carbon dioxide in a couple of seconds, and you get a geyser. And beautifully, it shoots higher up a mountain than it does at sea level, because the thinner air up there makes it even easier for the gas to break free. So that is the gas, and how it escapes. Now the third knob, which is the one nobody sees coming. How fizzy a drink feels is partly not about bubbles at all. It is a taste. In 2009, a team of scientists led by the Zucker Lab published a study in the journal Science showing that you have an enzyme sitting right on your sour taste cells called carbonic anhydrous, whose job is to grab carbon dioxide and turn it into acid right there on your tongue. Your tongue is literally tasting the gas as a kind of sourness. Mice bred without that enzyme could no longer detect carbonation at all. The fizz was, in part, a flavor the whole time. And there is a gorgeous proof of this hiding on mountaintops. Climbers who take a certain drug to fight altitude sickness happen to be taking something that blocks that exact enzyme. And they report again and again that champagne suddenly tastes flat and strange and awful to them. The bubbles are still there. The gas is still there. But the machinery on their tongue that turns fizz into a sensation has been switched off, so the sparkle just vanishes. They call it the champagne blues. Even the sharp bite of a fizzy drink, that little sting, is not really the bubbles popping. Researchers carbonated water and had people taste it under such high pressure that bubbles physically could not form at all, and the bite was just as strong. The sting is carbonic acid setting off the same nerves that carry pain and touch in your mouth, which is why the tingle keeps going even after you have swallowed, and there is not a single bubble left. You do not feel the fizz because bubbles are hitting you. You feel it because it is quietly chemically burning you, just a little, and you happen to love it. A couple of last twists for the road. If your big plastic bottle always seems to go flat, blame the bottle, not the recipe. Carbon dioxide slowly leaks straight out through the walls of a plastic bottle, which can lose a real chunk of its fizz in a matter of weeks, just sitting on a shelf, while an aluminum can barely loses any in a whole year. And the strangest one of all, a diet soda is often fizzier than the regular sugary version of the very same brand, not because it has more gas, but because the sweeteners and preservatives in it act like a soap, lowering the surface tension so bubbles form more easily and the foam lasts longer, while the sugar in regular soda does the opposite and calms the bubbles down. So put it all together, and the question falls apart in your hands. There was never one thing called fizziness. There is how hard it was packed, set by a law from 1803. There is how warm it got. There is how scratched your glass is, and whether you shook it. There is an enzyme on your tongue, and a nerve that carries pain. The fizz you thought was sealed inside that bottle is really being assembled in the moment, half in the drink and half in you. So the next time one drink erupts and another lies there flat, you will know it was never as simple as more gas. You will think about the pressure and the temperature and the tiny scratches and the enzyme quietly turning gas into sourness on the tip of your tongue. The sparkle was never only in the glass. Half of it was always in the person drinking it. And now, at last, you have watched it happen.